Thanks for the invitation. So I'll be talking about strong cosmic censorship. Recently, there have been many works about violations of strong cosmic censorship under certain setups, and most of those work have been classical in nature. So now, what we want to understand is whether what are the constraints a quantum state must satisfy if we want the quantum state to be smooth across some null surface. So we'll try to develop that. Basically, we'll show that we can define modes near the null surface, very close to null surface, and these modes must have correct entanglement across the surface, and have essentially these modes should have correct expectation value of 2-point functions, and this will give us a test which we can apply for on the Cauchy horizon of Reissner Nordstrom black hole or Kerr black hole, and determine whether extension beyond the whether this space-time is smooth at the inner horizon or not, and whether in some sense can we extend beyond the inner horizon or not. So
what does it mean to talk about the smoothness of a state at cosmos?
Yeah, I'll tell you that. Just so so suppose we have some null surface which I'll call which in some coordinate system. So let's say this is my space-time and I'm interested in some point on the null surface, and in some coordinate system around this point, this null surface is at u equal to 0, and in fact in that coordinate system I can write the metric as I can choose a coordinate system in which the metric is minus du dv plus some delta alpha beta d xi alpha d xi beta, where these are transverse coordinates, and there would be some corrections which I'll call this dx mu dx nu. So, and this point is essentially when all x denotes all the coordinates, and this point is essentially when x is 0. So this I can always do, and moreover this g should be such that this goes to 0 when x goes to 0. So all I'm saying is that so all we are demanding is that the metric across this surface should be continuous, and nothing more than that. It need not even be differentiable. So this is the metric we'll start with, and then we will define modes by integrating over the field in this region and in this region. I'll do that properly, and then show that these modes should have correct 2-point functions. Yeah, these x are just all the coordinates. X could be u, v, and zeta. No, these are not the new coordinates. These are just same coordinates. So my space-time is let's say d plus 1 dimensional. So zeta. So these are this is first coordinate. This is second coordinate. These are d minus 1 dimensional coordinates. D, xi, and these x's just run over all of them. This is just schematically written so that I mean we are mostly interested with this part, and this is some correction to it. Right. So the precise assumption which we want to make is that in the short distance, yes.
We are considering the first order corrections.
No, this is just a 0th order correction. This won't be important for our calculations. So precise statement which we want to make is that if you're looking at a 2-point function, let's say we are looking at phi u1 v1 zeta 1, phi u2 v2 zeta 2, and we are computing this in some quantum state psi, then what we want is that this should be proportional to where and some normalization where S is just
You're talking quantification in physics background, right?
sorry?
Quantification in a physics background.
Yes. So in the limit when x goes to x prime, x denotes all the coordinates. x1 goes to x2. We are demanding this, and plus there could be some terms r which would be less singular than this term. So this is the leading order singularity, but there could be other terms which are less singular than this.
If phi fields are free fields in this background?
Not necessarily. Yeah. Okay.
If they are free fields,
Yeah.
then from this you can calculate what is the expectation value of stress tensors.
Yes.
And then the fact that through the Cauchy surface your stress tensor diverges says already some structure about this quantity, some differentiator function
Yes.
version of this quantity.
Yes. So the fact whether stress tensor diverges or not, that is a very complicated calculation. So this, so we'll use this to derive some results which would be much easier to implement than computing the full renormalized stress tensor. So, and generally what we do in the stress tensor calculation is that we separate the 2 points and then we regularize the stress tensor, and then we take the points going close to the inner horizon, and that is how we calculate. But here we are doing something slightly different. We are always very close to the inner to the null surface. I'll explain why. Sorry? Yeah, properties.
So, if you think of this, let's say in flat space,
Yes. So
and
yes.
in conform field theory, where you have inserted 4 operators, and you're looking at the channel where phi comes and you get the most singular term there. It should be dictated by the identity, so it would care about the dimension of phi. Just to the power delta phi. Something.
D minus 1 by 2.
Why do you it's not a free field, right?
It's not a free field.
I think he's imagining a theory that in the UV is free. I think he's imagining maybe it's an RG flow from a field theory. That's at least that's how I do it.
So I shouldn't think of it in conform field theory? This is not a conform field theory.
No, this is just in any usual quantum field theory.
So in particular in conform field theory.
So D minus 1 by 2 would be your roughly the dimension.
But he's not saying this, right? He's saying phi can be anything. If he says that, then I will stop.
I mean, he's asking, you're writing formulas that seem appropriate for a field that is free,
Yes.
or at least free at short distances. Are you restricting tensions to such cases, or are you working? Would this work in Wilson-Fisher theory also?
That also D minus 2, but not D minus 1.
But he's working D plus 1 space.
So this.
Why do you want this singularity?
So this singularity can be motivated from the fact that if we, for example, if we look at flat space, and then we look at 2 points very close, and we just compute the 2-point function,
Yeah.
then this singularity should is just exactly that behavior
For a free
That is
for a free theory.
That is not true for a general operator.
Uh,
The universality which is coming there, you're saying.
Yes.
Is it model independent? I take any Lagrangian for phi, fixed background, and I solve equilibrium motion, I should get this.
No, of course you would, right? Wilson-Fisher theory doesn't.
Yeah.
So I mean, I think he's restricting attention to theories that are free in the
yeah, in some situations.
And computing this in the
He's looking at short distances.
Also, are you interested in taking like U across the horizon?
Yes.
Like concentric
Yes.
horizon?
Yes, that would be important. Okay. Fine. So now I'll define my modes. Just one more thing here. Delta U is just
State information paradox by saying that you are working in Andrew-Hawking, you ask for regularity of the horizon, and in that case this structure will follow. So it's like reversing back that procedure, where you will say that now stress tensor diverges, so it will say something about the structure.
Here I've put a regulative I epsilon prescription because these are really Weightman functions which we are looking at. So in t coordinates, the I epsilon prescription should give me t minus I epsilon squared plus x squared.
So U1 and U2 are the coordinates of the modes which are just.
Yeah, these are U1 and 2. So yeah, and in fact we can check that if with this prescription we'll get the correct commutator. So if we for example look at del U1 phi, del U2 phi expectation value and try to compute this would be correct with this prescription. So now what we want to do is that.
Description you are giving some order.
Yes, exactly. Weightman ordering.
What is the order? Or
Just this. So now first I'll define a tuning function in U. So first of all, I want to define my modes close to U equal to 0. So
That in U and V, it's basically if you look at time.
Yeah.
It's saying time of 2 is earlier than time of 4, right? Which is why 2 comes to the right.
Yeah. So so we are interested in integrating in a region very close to the this null surface. So I'll introduce two scales. One is UL, which would be much less than UH, and which itself would be much less than any scale. Let's say the curvature scale at that point. Let's say we call that R. So these both these points UL and UH are very close to the null surface, and we'll just for future use we will in fact introduce one intermediate scale U0. So yes. So and now we are defining a tuning function which has support only over this small region.
What is U capital?
Sorry.
What is U capital?
U capital is this is U capital. Everything is U capital.
One of the coordinates.
It's just one of the coordinates.
U small n is
Oh, this is let's say this point UL. This is UH. Sorry. So this and I will define the Fourier transform with this. So sorry. And in fact S nu is this. So so what we are doing is that we are defining a tuning function which has support only for this small region, and we are Fourier transforming in some sense in this U over U0 coordinate. And what we want is that this S nu d nu, this is a condition which we'll impose, should be 1. Infinity. And this should be sharply peaked at nu equal to 0.
Did you want a T on the right hand side of the second formula? That was the second formula was an inversion of the first formula?
Yes.
Is there a T of nu, T of u?
I don't want a T. I'm Fourier transforming in these U coordinates. So essentially, I can call x as e to the power x as u over u naught. And then this is just like e to the power iota.
Wait,
That's your cardinal, right?
the first thing is saying that this T is Fourier transform with Fourier mode S.
Okay, fine. Oh, sorry.
Oh, snap. No, don't you want
T minus u. T u. Sorry, T u.
Yeah.
Sorry.
Yes.
And actually, this is true for u greater than 0. If u is less than 0, then we will need to modify this a little bit. What we can do is that we can just write minus ul to minus uh du over u. U's and v's are this. All of this is u. V would hardly enter anywhere.
Except for that inequality that is v greater than 0.
This is also u.
Okay.
I'll point out whenever I write v. Oh, sorry.
What is T, please? T of U is what?
So T of u is just I'll just
Any
write
function?
any function which has support.
You're doing some Fourier transform.
I'm doing just some Fourier transform, and this T of u is such that when I do the Fourier transform, this function s is sharply peaked at 0.
So you're basically writing U is equal to e to the power I omega
Yes.
T prime or something.
Yes.
That is a standard.
Yes. So and this yes. Only over a very small interval, but note that this function is oscillating very highly around that because u is going to 0. So this function is oscillating rapidly at, in that interval. So we can actually extract out modes from this.
Small interval is probably infinite range in the new way.
Yes.
Exactly. So, no, but for S to be square integrable, you probably need T to be really compactly supported in that
Yes.
interval U, L, V, H.
Yes.
And all the functions T that you will consider here.
Yes.
I didn't understand your sign. So UL and UH, these are U's, right?
Yes.
So UL and U low and U high, both of them are positive.
Yes.
So they are not the 2 points around this U equal to 0 line.
So currently, this is just 1 point. This is just 1 point. Let's say it's at for u greater than 0. For u less than 0, we can just define the same thing like this.
But both UL and UH are on the same side of the that's how
Yeah, but those are just cutoffs. I can here I'm using minus ul and minus uh, so now it's the opposite side.
So, I'm sorry, what do we mean by 1 point?
What do we?
Mean by 1 point?
Uh,
UL and UH.
so,
I think it means
yeah,
one side.
one side. So this definition can we can so this was, let's say, on the side where u is greater than 0. So this definition is on the side where u is less than 0. These are identical definitions. So
Then U is never going to 0, right?
u is never going to. Fine.
And what does this scaling function do?
Yeah, we'll come to that.
So U and V are x plus t and x minus t.
Yes.
So how is it that I epsilon prescription is minus sign both?
Because we want delta t minus iota epsilon.
Yeah. I
And
think he basically wants the imaginary part of time of
Yes.
U to be larger than the imaginary part of time. of
Exactly.
one.
Yeah, but that will give a plus sign that is the second equation.
No,
T plus x and T minus x.
so t is like
That's what I started.
u plus v.
Sorry. No, I think it's T plus x.
V is like t plus x and u is like t minus x.
So this integration range is determined by U low and UH.
Yeah, these are my
UL
cutoffs.
and UH.
Yes.
Now, depending on the signs of UL and UH, you'll get this formula. So when you write U greater than 0, you really mean UH and UL greater than 0 for the first one?
No, ul and uh is always greater than 0.
Okay.
And when I say u is greater than 0, then my integral is over positive limits from ul to uh. When capital U is less than 0, then my integral is over minus ul to minus uh.
So in every side you have one definition of S. So there is this line U equal to 0. you can define one function S below that and one function is above that.
It's the same function. This tuning function is also the same thing. So here I have defined my tuning function in S for u greater than 0, but I can do the but I can use the same function and define everything for u less than 0.
Symmetry of T of u?
Yeah, we can just transform u to minus u. We can, let's say, we define a new variable x which is minus u, and then we'll get exactly this.
Oh, that's very nice.
That's it.
The ratio u by u0 will not pick up sign, right?
No, it's this is.
So whatever is in the bracket to the power minus I nu, that object should not pick up sign if it's just u into minus u from the first.
Yeah, this won't, right? If we go from negative, so here u is negative.
Because of that thing, ul is less than u0 is less than uh. Now if I just put ul and uh as negative, then u0 also should be negative.
u0 is always positive. I've already taken a minus sign over here. u0 is always positive. So here u is negative, but this whole thing is positive.
Okay. Yeah, I was just confused. So in the second definition, that thing is not there.
That thing is always there. ul, uh, and u0 are always positive. U is negative here. That is why I've put a minus sign here. So this whole thing is positive still. So this one. Fine. So now we can define our modes. So let's see, this is. So this is how I'm defining my mode. This looks complicated, but it is not. So essentially what it is doing is that it's just picking the part which is u over u naught raised to power plus iota omega naught from here. That's all it's doing. And normalizations have been set so that we will get alpha dagger is 1. So we'll check that. Sorry? This? Yeah, because so for example, when we compute alpha dagger, we can show that. So this is present so that we essentially are picking only this particular pole. I'll show that. Just before that, I'll just write one more definition.
You said V equals 0
Yes.
because it's like because you just want the coefficient of the modes. You don't want
Yes.
that oscillation in V. Is that right?
Actually, derivative will kill that oscillation in V. So we are also taking derivative with respect to u. So we are so this integral is over du and d minus 1 psi over a very small patch around this surface.
Yeah.
And even the transverse coordinate we only need to integrate in a very small region.
I see. No, what I was asking was this: if phi was an arbitrary function, not some on-shell function,
Yes.
we would have a different mode function, different mode coefficient, depending on the frequency in u and the frequency in v.
Yes.
So you're losing a lot of information then by setting v equals 0.
Yes.
However, if it was some on-shell field,
Hmm.
then presumably if you know what u is doing, then the on-shell condition tells you what v is doing. So you're not losing information by doing this. Is that, am I thinking right? Why are you saying v equals 0?
I'm setting v equal to 0 because this is not really important. Setting v equal to 0 is not that important.
Okay, so you're saying it's a small region of space?
Yes, that's all I'm saying.
Everything is effectively constant in everything except
What will happen is that if we, so we can define modes very close to the this surface. These would be like the Rindler modes, and those will, so one would be like e to power iota omega naught omega, and the other would be v to power some minus iota omega, something like this. And so what we are doing is that we are just picking this one. So close to the surface, we can always define our modes to be something A and B.
Yeah, and the reason you don't have u to the power I times v to the power something else is that you're looking at on-shell degrees of freedom. Right? These are solving some wave equation.
Yes, these are solving some waves.
Right.
And I mean, that is how we'll, so if we write,
I'm just saying that were you looking at an arbitrary function of v and u, not something solving a wave equation, you'd be losing information.
yes, yes, agreed. Yes. So, but we are interested in this.
Yeah.
So,
This is like the UV part of the momentum. Roughly alpha captures the UV part of the momentum in some sense. It's very small distance in space, but T had support. T had support only in a very
Yeah.
small thing.
yes,
And then you are picking the derivative of I only from that part. So
yes.
Only from that part, but he's keeping the dependence at zeta, but not at v.
Zeta is also I'm integrating over a small region.
So, yeah, so why are you treating v and zeta asymmetric?
So V I can think of as my, some sense my time coordinate, and
Yeah, I think I understand.
yeah. So this equation was for u less than 0. So if u is increasing this direction, u is 0 here. So this equation was integrating in this region, this equation. Now this equation is like integrating in this region. So and this minus epsilon is only important because we want these to be space-like separated. So when we compute the commutator, then it's alpha tilde is 0.
And T of u was some prescribed function, some given function?
No. It's just some arbitrary tuning function such that this is true.
Right, so, but it's got nothing to do with physics, something
No.
you specify by hand.
Yeah, and we are not going to even specify that function.
You just basically want to throw out everything away from that.
Exactly. I'm only looking at things close to the horizon, and the claim is that that will give me some condition which must be satisfied for the horizon to be, if we want the geometry near the horizon to be smooth.
And just again, T of u is non-zero between ul and uh.
Yes.
Okay.
And beyond that, it's zero.
Yeah, so it's a filter.
It's a filter. Yeah. Right.
I'm sorry, sir. Why are we defining the modes in terms of the tuning motion?
This won't really play a role. This is just there to extract the near the behavior near the null surface.
It's some function which ensures that the
No, this doesn't ensure anything. So the properties of alpha and alpha tilde will ensure that we have smoothness at the horizon. So
so why are we introducing T of u?
so that because you see, if we solve the wave equation and write down the modes, then very close to the u equal to 0 surface, we can write our mode expansion like this. So what we are interested is basically extracting this. So we want to say something about this. So that is why I'm choosing T such that we are only extracting that part in some sense.
Okay, so it's related to the density. Meaning what is A?
What is?
It's the
A is A is the annihilation operator corresponding to this mode, and
so
B
you
is
are
another.
expecting some annihilation operator
Yes.
outside and inside.
Yes.
And the claim that they commute is some sort of a claim about the nature of the horizon, nature of this u equal to 0 surface.
No, I mean that is just the claim of causality. Space-like points should commute. That's all. This,
That's the volume in the z direction, I guess. That's what's,
and this is omega.
that's omega 0. What is the curve?
Before omega 0.
Before omega 0.
Pi.
Oh, it's pi.
Pi.
I'm sorry, why are they space like
Because no, because I've chosen epsilon to be less. So v is increasing in this direction. So I'm choosing this and this. So these we can just see that these are space like separate.
And you're focusing on the 0 more than zeta for some reason.
Not really. So,
Why? Are you integrating on the zeta?
but only over a very small patch
Patch of what?
of theta. So, for example, if it's just one coordinate theta, then I'm integrating, let's say, over around theta naught, some very small, around theta equal to 0, just minus.
You told us that there's a separate, that integral goes over some small integral.
Yes, this integral goes over some small integral in theta, and the volume of that integral is v theta.
Okay.
So currently I'm not assuming any symmetry in my space-time, but if the space-time is symmetric, then I can actually do this integral over all of zeta, and then introduce some y LMs over here, so as to pick up some particular spherical harmonic. So currently I'm not doing that.
So this v at any u v equals to 0 and v equals to minus epsilon makes the points space like. Is that right?
Yes.
So facility will go through for let's say future event horizon it will go through. So far there is no other assumption.
Yeah, there's no other assumption. Fine. So, yeah. Now, the 2-point function which I wrote down, we can actually consider this del u1 phi u1 v1. So this would be just this I'm just differentiating with respect to u1 and u2, and this will just give me some d squared minus 1 by 4 into whatever the normalization was over s raised to power d plus d by 2 and some delta v squared. That's other terms which are less singular. So I'm just I took the 2-point function which I erased right now, and differentiated with respect to del u1 and del u2. Now, the claim is that in the limit, when if we take the limit delta v going to 0, then this quantity. So this, let's look at this quantity. This quantity is like delta v squared divided by minus delta u delta v plus xi alpha delta xi beta sum b plus 3 by 2. So this quantity, if we are taking the limit delta v going to 0, then this is 0 unless this is also 0. So this will kind of this will essentially give me some delta function in the transverse coordinates.
That is a delta.
Which this is a metric. Let me call it eta.
That coordinate is delta xi.
Yeah.
So we are so xi alpha was taken to be some infinitesimally small coordinate.
Here was what we are doing is just looking at this 2-point function for points very close by. So that's all we are doing. And but what we are doing is that we are taking the limit where delta v goes to 0.
That should be xi alpha.
That should be.
Xi alpha. Rather than delta xi alpha.
So I remember that we defined our coordinates such that xi was going to small difference between that point, and xi was going to 0 in for the point we are looking at, in the neighborhood of the point we are looking at. So this is just the difference. This is just just s, the geodesic distance to leading order. Because we are differentiating with respect to v, with respect to u. So when we differentiate with respect to u, we'll get this delta v, which is because of delta u into delta v. This power has also changed, so I think it's fine. So this was initially it was d minus 1 by 2. Now it's d plus 3 by 2.
Yeah, so that is increase of 2, right, which is
Yes.
derivative.
Yes, and here we have to.
But it's a derivative acting on a square function. S square.
So to extract this coefficient,
And there has to be a delta V for boost charge. Delta U carries boost charge. Del.
Yes, but in this definition, what is the T outside in the denominator? Alpha. Definition of alpha. What is the T sitting outside?
t,
Yeah.
That is pi.
this is pi.
By square.
Oh, so but then your definition becomes independent of it.
Yeah, yeah.
Okay.
S is delta. That's right. Yeah.
I mean t is here. That's all.
But I'm saying that your creation adjacent operator seems to depend on your tuning function, which is some arbitrary function, right?
Yes, but it's arbitrary in the sense that this is satisfied, so it really doesn't depend on d. I mean, it.
So will it really drop out, or
Yes, it will drop out.
but,
It will be drop.
okay.
I'll show you. So to compute this,
This is a precise formula. This integrates. If I integrate this.
yeah. So I'll write down the precise formula. Just 1 minute.
Roughly the Lorentzian of zero width is the delta function. And I thought there was normalization.
So we can. That is what we are demanding. The leading order divergence. Leading divergence is independent of any state. And this will just turn out to be. Okay, so what I've done is that first I've changed variables from delta xi to, so x is just root of minus delta u delta v, and I've just pulled this out. So I'll get minus delta u delta v raised to power d plus 3 by 2, and because of this, I'll get in the numerator d minus 1 by 2, and that will cancel to give me delta u squared into delta v squared in the denominator, but that delta v squared cancels from here, so we are just left with delta u squared. And then this integral, so note that this integral was over some finite, very small region, but because we are looking at delta v going to 0, so these directions, these integrals would essentially become over an infinite range. So we'll get something like this. Now this mod x variable goes from 0 to infinity, and we'll get some st minus 2, and we'll get this. And in fact, when we plug this here, what we'll get is in the limit delta v going to 0, this 2-point function del phi del mu phi. This is just minus 1 over 4 pi 1 over u1 minus u2 squared. And remember, there was always this I epsilon into delta d minus 1. We'll get this.
Okay. I should have expected this for some physical reason.
Yes, because the imaginary part of this will give me this thing we can write as, and the imaginary part of this would be like delta prime u1 minus u2.
Yeah, sorry, I'm asking more elementary question. Why should I have expected that the two u derivatives of phi
Yeah.
should have been very local? Why should I have expected that expectation value to be non-zero only with the 2 points say coincident transfer space? This is something I should have known.
Only at delta v equals 0, right?
Yeah, that is only at delta v equal to 0. It's
Right.
only in the
So
limit
equal
delta
time.
v.
So let me think of v as time.
Yes. Then also we'll get something like this.
Right. So I'm looking at equal time correlators.
Yes.
And equal time correlators, oh, that's what you're saying.
Yes.
It's sort of like causality, right?
Exactly, it is causality, because see, the imaginary part of this is related to del phi commutator. So the real part will just cancel. The imaginary part is related to this, and without the derivative, it should have been delta u minus u prime and delta of other coordinates.
Sorry, I didn't understand the imaginary part.
So this we can do a principal expansion. Just write it as something plus imaginary part, and so we would have expected this, but when we are taking derivative with respect to u here also, then we basically accept delta prime.
But the surprising thing is that it's not just the commutator. Even the anti-commutator is non-zero only at zeta 1 equals zeta 2, right? For instance, it wouldn't have worked without the u derivatives.
Yeah, it wouldn't have worked without the
So
u.
it's not purely some causality thing, right? It's something I should have known, I think, but I don't know in what language.
For this abstract, if you are doing this analysis near the future event horizon, where the psi state is the undo vacuum.
Undo vacuum means the vacuum in.
Nothing is coming out from future null infinity. So this is the state psi, and you are doing an analysis near future event horizon, and this is phi is a free field. So where you can calculate all the expectation value of the Pearson analysis operators if you want, then you can check this is true.
Yeah, but even without creation annihilation operators, this is just 2-point function in flat space and slicing along nice lengths, right? And he's observed that this 2-point function is non-zero only at equal times, at equal zeta, when you take these 2 points like separators, the Weissman function is non-zero only at equal zeta. This is true in flat space, and in Cauchy space. This is something I feel I should have known, or that I know in some language. I didn't know it. Now that he's saying it, I can't relate it to something else.
It's exactly on the null surface. It's not even inside or outside. It's
Yeah,
tricky
because delta
part.
v equals 0. And it works only for the del u derivatives.
There is the other derivative. You have taken v as
Yeah.
time coordinate. It's the it's the other null direction that you.
Yes.
Yes, and so this is a familiar statement?
It's a familiar statement from the analysis that I told you. This analysis, like based on this kind of.
First point of filtering chapter is
Yeah, exactly.
That's
Peskin,
it, yeah.
yes. So Peskin Schroeder knows this, but why didn't he tell me? I mean, okay. Yeah, okay. He has it somewhere. Yeah.
Property gives liquidity.
Yeah.
Okay. Yes.
For example, in 2D CFT, it's a free field, free Gaussian field in two dimensions. Then the fact that there is a contact term, this is the kind of thing that you have a contact term in this commutator between these two derivatives.
But it's more than the commutator. See, the commutator is sort of understandable because that's causality. You do this kind of like quantization, then things should commute across except at equal times, right? That's a familiar statement.
Even with the files, no difference.
Yeah, even with phi's, and I'm sure that will work out in some way. But what's interesting is that it works also with the anti-commutator. It's a statement about the Weightman function. That was new. That's somehow new. I'm sure I know it in some language, but I'm not yet.
Okay. Anyways, so we can now compute, for example, alpha dagger, and under these assumptions, this assumption in particular, and that nu is sharply peaked at 0, we can show that this is just 1. So, and similarly, alpha tilde dagger is just 1.
Wait, now by saying you can compute it, what do you mean by that?
So I'll just
You use this Weightman function,
yes, I'll use this.
you use that result and then use that to compute.
Yes, essentially, yes.
Okay.
So all I'm using is that it's just this, that phi pi is iota del kind of thing.
Pi. Oh, is pi?
Pi is like del u phi. So yeah, that is what I was trying to say. So pi is like del u phi because v is my v is my time coordinate in some sense. So this is just, it's probably that answers your question.
No, but it still doesn't answer why it works for more than the commutator.
Anyways, so we can check this, but let's now compute the expectation value of alpha and
Alphas, are they functions of zeta?
no, they have been, I mean, in some sense yes, because it depends on which region of zeta we have integrated over. So yes, they are in some sense.
So they add over different little bits there are 0.
Over, sorry, I didn't get that.
You integrate over small regions in zeta.
Yes.
So if I do this alpha in region 1, commutator alpha dagger in region 2, I get 0.
Yes.
That's effectively a delta function. Yeah.
So yeah, now we can compute the 2-point function, which is the important result, alpha tilde. So this I'll just write down. So this will give me some pi omega 0 v zeta, and we'll get some expectation value of these two expectation value, and that is just this minus 1 over 4 pi 1 over u1 minus u2.
Alphas are functions of omega naught.
Alphas are functions of omega naught, but I have suppressed it.
Writes that.
Yes.
Alpha of omega naught.
Yes.
Yeah.
Basic question, what is the rationale of splitting these modes into one region of space and the other region of space? We consider these modes, at least if you consider this standard quantization, just have mode defined on some given space-like surface, right? Here it's light cone, let's say, so it would be the whole light sheet.
No, this integral is not over the whole light sheet. It's really.
So okay, modulo this small region business, but it should be, why is this, you are doing integral on one side at one point and find the tilde thing?
So in some sense, because we want to extract out these kinds of modes, and these appear, for example, let's say if it,
using somehow that the Hilbert space factorizes between that Hilbert space and that Hilbert space, you are finding a basis for that Hilbert spaces.
no.
And then expressing the state
then that analytic continuation would give us only one side of a Reissner wedge. Okay. So, though if you did you did a quantum field theory in that kind of language, which is in some sense the natural thing for the exterior of a black hole, because the Euclidean direction for a Euclidean space for a black hole is a cylinder, in which the Euclidean time direction shrinks. So the angle of the cylinder becomes tiny. Okay, so just in field theory in quantum, if you work in sort of short sheet type coordinates, what you're doing is taking Euclidean space and continuing angle to be tiny. And if you did that, then you would very naturally be forced on one side of your line sheet.
And what am I supposed to do with the
Then that's a matter of what your vacuum is. So so one question you could ask is, suppose you take the other vacuum, the vacuum where time was time. Then you've got a nice smooth vacuum all through. And then you could try to express that vacuum in terms of these modes.
Yes.
The modes where acting was time. That's the kind of game, roughly.
Sorry, so what was your question? What was your question? No, my question was that how is it that we are talking about two kinds of modes on one light sheet?
Abhijit saying you're doing something very artificial, right? You've got R11, and then you're taking a light sheet. From point of view of quantum field theory, it's something we'll never do. Right? You look at modes here, you look at modes there.
Yes.
You would just look at modes everywhere.
Yeah.
Why? That's the question.
This Pushkal and then says
Yeah.
Right. But this, you can just say this purely in quantum field theory language. It's two different words. Analytic continuation of the Euclidean space. You can think of this as expressing all in that, in the modes where you make activity. Roughly, I think what he's doing.
And then the other side is what?
Now you're saying that there's the other side, which is actually what he gets is this and this, and then the other side is not really there in the angle equals time.
Yeah.
Right. So that he will have to put in, by hand. It's like, the behind the horizon has no Euclidean angle.
Okay. So
Pushkal coordinates.
So we can use the expectation value of this expectation value and write it like this. And now,
Does this now also mean that now that I'm able to do this, does this mean I'm just on a space-like surface, I should be able to do this? On a space-like surface, I pick a codimension 1 slice, codimension 1 wall, and on this side I quantize differently with alpha, and the other side I have alpha tilde.
Yeah.
What is the principle that
Yeah.
sometimes I'm allowed to? Is that only if I have a map to some other space?
Well, in a way you are doing that, because you see these two things meet on there is a space-like surface that goes through the region, namely at t equals 0. So if you just quantize on that space-like surface, you could do both quantizations. You could do time as well as the angle, which works everywhere. So in some sense, locally, you could take a space-like surface and then divide it up into these things.
In Minkowski space.
Even in Minkowski space. Right? So take Minkowski space, take t equals 0.
Yeah.
That's a space-like surface. Now that space-like surface, half of it lies on one edge of the Reissner wedge, the other half lies on the other edge. Okay? So you could quantize it here, and you could put together the modes where this guy is time in terms of the modes here and here.
Yes.
I mean, I don't know exactly what he's going to do, but I think that's roughly.
yes.
one fun fact. This Andrew vacuum, or let's say thermofield double.
Which is Andrew vacuum here? Is it the one where global time is? So which is Andrew? It's the other one.
The global time in Andrew is thermofield double.
Thermofield level, yes.
This is the one we do calculations.
Yes.
So prepare by path integrating.
Yes, exactly.
So let's say thermofield double state.
Yes.
In thermofield double state, if you take a trace tensor and integrate over this kind of null line, that expectation value is exactly 0.
Take stress tensor and integrate over
A null line.
which null line?
Let's say you stay outside the black hole and take a null slice, which will cut through the, let's say, white hole. If you integrate this trace tensor and take expectation value, it will be 0.
Okay. Let's move forward. So we can write this, and we can.
You want to see the entanglement between outside and inside. This is why you are talking.
Yes. So we can actually use this identity, which is easy to see in some sense. Okay, this is an identity which is easy to see because essentially we'll pick at poles, and the poles are it's omega going to minus I n, and we can just convert this integral to a sum, and then we can show that this is true. And this is well defined because even at infinity and minus infinity at both omegas, this is going to 0. So it's a well defined integral, and we can use this to see this form here is the form which is important to us, because this is exactly the form. Now once we substitute this here, and we'll get some u2 integral, and see this u2, there's a u2 over here, and there's a t over here. So this it would be something like this integral, and it would give me s of that frequency, and this s is really like square root of a delta function, because mod s squared del nu is giving us 1. Similarly, u1 will also give me something like that, and essentially when we just plug everything in here, what we'll get is that alpha tilde would be integral s omega minus omega naught squared into e to power omega e to the minus pi into d omega. So in the limit when this s is really sharply peaked around 0, this will just give me e to power minus pi omega naught divided by 1 minus e to power minus 2 pi omega naught.
Sorry, please tell me again why you wanted s to be sharply peaked around 0.
Because otherwise we won't just get this. This really we want to think of as a delta function.
Yeah, but just in your original logic, you wanted something peaked in U space, right? I thought. Yeah,
No. This U was had support over over UL and UH.
And those are thought of as large?
As large. So this U had some support.
So in the limit that UL and UH go to infinity.
Infinity.
Then
and
S becomes sharp.
Yes. This becomes a delta function. So we'll get this. Now, but
more precisely, UL goes to 0 and UH goes to infinity.
Yes. And now we want to, we can play the same game for alpha omega naught, alpha dagger omega naught. And there again we will end up with these integrals.
And this I should think of as a Bose factor.
This is some Boltzmann factor, yeah.
Bose Boltzmann factor.
Yeah, this one will give me exactly the Boltzmann factor, because now when computing this, what would be important? So this computation is not here. This iota epsilon prescription would become important because we basically to get this guy we used this formula of picking the poles, but when we want to use compute alpha dagger, then essentially this integral would be like would not have a minus sign. So what is happening here is that this for every alternate pole we are getting a minus sign, and this minus sign is being cancelled by this e to the minus pi omega. But when we don't have this minus sign, then we don't need this. So then there are really then we have like many options. We can either put 1 over here or either put e to the minus 2 pi omega over here. So how do we decide which to choose? So that is set by this I epsilon prescription, because this will basically we are adding some phase, and that so that this integral makes sense both at minus infinity and plus infinity, and that's how we'll fix this, and we'll get 1 minus e to the minus 2 pi omega naught. And similarly, a dagger ray will be just e to the minus 2 pi omega naught over 1 minus e to the minus 2 pi omega naught. So
And you never kept track of Gray-Waddy factors. This is exactly the derivation of Hawking radiation, right?
yeah, this is the derivation of Hawking
And you
radiation.
just kept track of the 2 dimensions. If you have this extra dimensions, which is small,
Yes.
you should have kept track of Gray-Waddy factor.
It's just working in flat space.
It's totally so far.
Yes.
I mean, I am also not very much convinced that you didn't make any assumption about the horizon. That if the horizon is not smooth.
So far, horizon hasn't even come in, right?
So say there is a large quantum fluctuation at the horizon, and then your semi-classical calculation do not.
Yes.
make
So
sense.
the question which we want to answer is that if given a null surface which is smooth.
So given an answer requires you to make sense of gravity in a semi-classical.
Yes. So what we want to answer is whether this in this strong cosmic censorship works. What people are claiming is that the inner horizon is actually we can extend beyond it, so it's smooth in some sense. So if it is smooth, then this is a criteria which must be satisfied.
Smooth, okay. Not smooth, but okay, continuous.
It's continuous. So here also we only demanded continuity of the metric and fix the 2-point function, leading order singularity of the 2-point function. So note that doing this doesn't directly imply that the stress tensor doesn't diverge. So this will only imply that the leading order stress tensor won't diverge in some sense. So we are just looking at the leading order divergence of the 2-point function, and using that to fix this particular entanglement.
So if you calculate renormalized expectation value of stress tensor in high state,
Yes.
So far with the assumption the metric is continuous. If you calculate the expectation value of stress tensor
Yes.
in state high
Yes.
with suitable regularization, then what would you get?
Sorry, what is state psi? The state in which these 2-point functions
He is
work.
doing
Yes.
every calculation.
Yeah.
So we can only say that the leading order divergence of this.
Leading order in what?
Actually, why is that divergent? Isn't this just the state calculation as in flat space?
So
Yes.
Exactly.
So there should be no divergence over anything, right?
This is why I am trying to push the. What is the extra assumption that is going? Sorry.
The extra assumption.
So far, whatever you have done, it's entirely same as
But then you renormalize it away.
Schwarzschild, that's all.
You
Yes.
And in the future.
Yes.
You
Yes.
didn't make anything extra.
No.
So why will this extra divergence
Yeah.
come in?
So take the usual subtractions in flat space, we'll get it. There's no further physics.
Oh, why the extra?
So far, the calculation.
Yes.
you have done,
Exactly same as.
Say you are doing a Schwarzschild black hole, and
Yeah.
you are doing this calculation near the future event horizon.
Yes.
Every thing that you said will go through.
Yes.
So
Yes.
now to say something about we already know that near future event horizon for Schwarzschild, stress tensor, this is not going to diverge. It will diverge only when you go to the Cauchy horizon in
Yes.
Reissner Nordstrom.
Yes.
So we want to see the difference between the.
Yes. So let's say we impose the condition that these criteria, this condition is satisfied at the outer horizon. Now we want to see, given this, can the inner horizon also be smooth? That is the question which we want to answer. So that is a non-trivial question.
That is a non-trivial question, but so far this calculation.
Yeah, this calculation is just
to event horizon, future event horizon.
Yes.
You have also separate question that given the event horizon is smooth,
Yes.
what can you say about Cauchy horizon?
Yes.
This is a separate question. But
Yes.
stay near the future event horizon.
Yes.
There, if I ask from this calculation, can
Yes.
you calculate little bit more and say something about stress tensor?
That should be finite, right? But
I
Yeah.
think this test is that whether the 2-point function will behave this way or not, and not anything about the stress tensor.
see,
That-
so that should be finite. I'm saying should be because for the case of PTZ black hole, we can check that this criteria at the inner horizon is satisfied. But Harvey Real just claimed that the stress tensor in fact diverges for um, for non-extremal black holes. So, in some sense, yes. If that is true, if that statement is true. So, okay. Anyways, now I can apply. Yeah. What is omega naught? Omega naught is just the frequency of this annihilation operator. It's fixed by this. So because of this omega naught, but this omega naught could be anything. So this omega naught would come in here. Yeah, here.
Is it taken as a definition here or?
Is it?
Taken as a definition?
Yeah, this statement is taken as a definition.
Is it some function of? So what does it correspond into?
This is just picking out particular frequency. This is just picking out annihilation operator of frequency omega naught. So, okay. We can do this for example, if we look at Reissner Nordstrom black hole now, then we can modify this a little bit. In fact, what we can do is that, as I was saying earlier, we can pick a particular spherical harmonic, and let's say we are looking at points at the outer horizon. We can do this. And this, yes.
Can you just tell me what is the criteria of smoothness now?
Yes. So the criteria is that these alpha tilde should be e to power minus pi omega naught divided by 1 minus e to power minus pi omega naught. And similarly, alpha dagger alpha should be 1 over 1 minus e to power minus pi omega naught.
So does the top result tell me something about the entanglement structure of the particles across?
Yes.
Is it really, I mean, can I just see it directly? Is it directly related to this computation?
So this behavior, for example, from here we can in fact construct well pairs of operators and just
So if I
check.
take maximally entangled state and compute 2-point function of such thing, I will get that result.
So for example, this is the result we'll get in a thermofield double slit.
So far you just worked on one side of
No, this A tilde was on the other side.
A tilde.
So let's see.
Construct a vacuum to see explicitly whether
So in Rn black hole we have this kind of a structure. So this is, let's say, u equal to 0, and here u is defined as in region 1. This is region 1. This is region 2. U is defined as e to power minus kappa plus e minus r star.
so you're in ADS.
We are in ADS. So now in this region, very close to the horizon, we have modes which are essentially we have e to power minus iota omega u, these kinds of modes. T minus r star. So if we do a mode expansion over here, we will have modes which are A is my annihilation operator into e to power minus iota omega t, this whole thing, and this whole thing can be written as u to power iota omega by kappa plus. Similarly, because we'll have some boundary conditions, so we will have some phase and v to power iota omega by kappa plus minus iota omega by kappa plus. This would be my mode expansion in region 1. So if I now we can compute alpha omega naught using same kind of formula, and in fact we can choose a particular spherical harmonic. So this works indeed something like this. Then we can show that this alpha omega naught is just some this S is that same as into some phase we can show this. This just doing this integral. Similarly, alpha tilde omega naught would be S star e to power minus I theta A tilde omega, where A tilde, so A were the modes here and A tilde are modes here. So now we can compute alpha tilde, and we can impose that this condition is satisfied. What that would mean is that let's see. Okay. What that would mean is that now we can compute A omega, A tilde omega.
Sorry, I missed how you're going from A to alpha.
So we have a mode expansion like this.
That's A, yeah.
Yes, and we just plug this mode expansion into the formula for alpha. And those formula were essentially defined such that it would pick the A mode.
Dependence is there and you want
Yeah.
okay.
Yeah, so UV dependence in some sense is still there because of this function.
So the natural basis there was A, but now you want to go to
Yes.
your basis.
So this I'll call global mode, this I'll call local mode. So UV dependence is this tuning function dependence is for now still there. Now we can compute alpha tilde omega. So let's say this 2-point function was some A1 omega into delta omega minus omega prime. And in fact, I'm suppressing the angular momentum part, but otherwise there would be delta L prime plus some A2 omega comma omega prime. Now I'll plug this when I compute alpha tilde omega. I can plug this here, and this note that if we assume that this is smooth, this part is smooth, this part is not diverging, which is a reasonable assumption, then this computation will just fix this part, A1 omega to be e to power minus pi omega by kappa plus over 1 minus e to power minus pi omega by kappa plus. So the point is that why we are doing that was basically to prove that even though this expectation value can have some corrections, let's say if we throw in some matter at a boundary, then the 2-point function won't remain exactly the 2-point function we expect in the black hole background, but that correction won't alter the delta function part of this expectation value.
Because that came from some very short distance behavior.
Yes. So the claim is that this thing is universal, and this in fact has to hold true for omega, which is small, large, for all L. So this should always be true. And this is a very simple test which we can just implement, maybe numerically, or just if we can solve the differential equation in some WKB approximation, then we can do that. So
The 2-point
Yeah.
function alpha cares only about the delta part of the
exactly,
global,
exactly.
not even the power.
No. it would only care about this, because
That is universal again. Why?
this is universal because we have essentially we demand this.
Demanding that.
We're demanding this.
Yes. But a priori,
So
which way do you want to draw the conclusion?
so I want so what I'm concluding is that if the null surface is smooth, so if the horizon, let's say we are currently working at outer horizon, so in the given quantum state, if the outer horizon is smooth, then this function should be exactly this.
Okay. And now you take that and apply this to region 2 or something like that.
Yes. So this has been applied to outer horizon. Now we can apply this to inner horizon. So for inner horizon, we have some modes which are like, let's say we are looking in this region. So these are modes like B, and let's say this mode is C across the inner horizon. So so we again want B dagger omega. This if the state is smooth at the inner horizon, then this should be minus 2 pi omega omega over kappa minus.
You have no control over C, right?
I have no control over C for the
C
moment.
could be absolutely anything.
C could be absolutely
You can
anything.
only impose this condition.
Yes, but now this we can do this. But now what we can also do is that we can write C as, let's say, some K. So B just before that. So this B would be some K1 A plus K2 A tilde dagger. By just solving the differential equation, we can get this, and this form would be satisfied at least as if we have time translation symmetry, because we are matching the coefficient of e to the minus iota omega t. So we can do this, and let's say C. In fact, we can write as A tilde plus K4 A dagger plus, let's say, some new modes K5 E plus let's say D plus K5 K6 E dagger.
So I haven't understood. You're defining some new modes.
Some new modes. So some new modes. So there's some contribution of these A tildes. So let's say.
I thought A tilde was defined only in region 2.
No. A tildes are just some operators acting on psi. So these A tildes, B's, and all these operators are defined everywhere. I mean, they are not restricted to some region.
U, V, and so on.
Yes. So they were extracted by looking in this region. So the point is.
Just time evolved.
Yes. So so we can now write operators, for example, B in terms of A and A tilde.
Sorry, A just goes right. A doesn't get that too.
Sorry.
A
It-
can go this way also. A doesn't
Yes, because in ADS we have this boundary condition, right? So this mode is also A.
E and A tilde will form a complete basis for, let's say, region 1 and 2. You have B there as well, so you can
So
express
explain
in
B.
terms of A and tilde. But your first line, what was the assumption in the first line?
This line.
Yes.
I've assumed that
That's his criteria.
this criteria.
This criteria is for what? That metric is continuous or metric is
Metric is
first
continuous.
differentiable?
Continuous.
So the claim is as long as metric is continuous,
This should be true.
this is the criteria.
Yes. So yeah, for C we can do this. These old write in terms of old modes as well as some new modes. Let's say we do this.
The new modes coming out of the singularity, right?
Yeah, some region beyond the inner horizons. We don't know much about that. So now we can do this, but once we do this, we can demand. Now we can demand that C B tilde. C B expectation value is just 1 over 1 minus.
So that'll just tell you something about the unknown modes.
No. So what will happen is that will fix that these modes can't be there. These modes cannot be correctly entangled with B. So if you want this to be satisfied, then what will happen is that K3 and K4 need to be fixed in a particular way, and these K5 and K6 should be 0.
A tilde modes going that way
A-
across the Cauchy horizon.
Yes.
And A tilde and that's A tilde dagger or A dagger? K4?
A dagger.
What is A dagger now? What kind of mode is it?
So A was inside here. A was going like this.
Okay, so mode going like that.
Yes.
Still on this side of the Cauchy horizon.
Yes.
Okay.
Yes. So we can think of this as some reflection of mode from.
I can't
let's-
understand what A means on the other side of the Cauchy horizon.
A, this one.
A dagger, yeah. It's a mode that seems completely defined only in 1 and 2.
Yes, yes. So these modes, this mode is defined using defined in this region. I mean, but
So why are you writing C in terms of that?
so but this I can think of as operator on the state on the CFD.
Defining in region 1 as a coefficient of a sum mode, which is totally well defined in region 1 only.
Yes.
But the operator that multiplies that mode, the Pearson operator, as an operator in the Hilbert space, that exists
Okay.
in any time slice that you do.
Okay.
I was thinking of them as operators.
Okay.
I'm sorry.
Yeah, as operators. So the question is whether we can define new modes once we cross this horizon.
You've got too many. I mean,
Yes.
these modes are not independent of each other.
D. I'm imposing D and E should commute with A and A tilde. So these are new modes completely independent of A tilde and A. These are some modes which are just in some sense in
But I thought
in reason.
Okay, so C would be modes that will. Wait, maybe you should go on. Maybe you should.
So
C and A tilde is a complete basis in 1 and 2.
Right.
Let's say in 1 and the one that he has not written 2 prime,
Right.
the one where it is bad. So in you need
let's
something.
call it 3.
Yes.
That's 3.
So here we need some extra modes.
So let's say B and C is there.
Yeah, the extra modes I thought were the D and E diagram.
Yes.
So C
Yes.
and B are complete in 2 and 3, but then C and A is not enough. Therefore, he needs something D and
E.
some D dagger.
D and E dagger.
Yeah. Okay, so something I'm confused about, but let's. Wait, what are you going to use this?
So now, yes, remove this. Before doing that, I just one more thing which I didn't say. So let's say
And C and B will commute or not?
C and
C and B.
B will commute.
So it's the like the usual kind of horizon separating them, and there is commutation.
Yes. So so let's say my, action of A tilde on psi was just one.
In the end, aren't you just computing the 2-point function
Yes.
of phi with phi in the thermophile double state near the Cauchy horizon? Is that in the end what you want? There's all a way of doing that.
In the thermophile double state, yeah, in some sense, maybe you can say
This is
that.
the short distance behavior that you are probing in some.
Yeah, you're looking at the state that is regular around the
Outer horizon.
event horizon, which is like the thermophile double state.
Yes.
And in that state, you want to compute the 2-point function
At the inner
at the
horizon.
inner horizon.
Inner
right?
horizon,
And
exactly.
you want to check whether that diverges or not.
Yes.
All these modes are in your head, right? It's just some analytic continuation of a Euclidean correlator.
Yes.
So they may be convenient for computation.
Yes.
So in the end, you're computing this 2-point function.
Yes.
Okay.
Yes.
Yeah. Okay.
And the B is maintained by saying if your 2-point function is like this, which is sort of you can derive by saying the thing that you with the theory is
Yeah.
free.
Yeah.
And the claim is that if it is like that, if the 2-point function is like that, then the modes are this kind of entanglement and this kind of thermal property.
Right.
Therefore, he is probably equivalently will look at those properties to draw a conclusion about these 2-point functions.
Just one more thing, which is important, is that let's say if we look at action of alpha tilde on this straight psi. Now we are currently, let's say, just looking at the outer horizon. So this, suppose we write this as alpha dagger psi, some combination of action of alpha on alpha and some new straight chi. Then what we can do is that first of all we can just now for example apply this alpha dagger to this, and note that this straight is orthogonal to these two straights.
Somewhere along the way you're going to have to solve the wave equation.
Yes. Yes, and that will fix my k1 and k2.
Okay.
So this statement needs to be checked. This statement, whether it's true or not, needs to be checked, and in fact it's not true for RNADS.
Okay, good. So
For BTZ it's true.
Okay, fine. Okay. So this you've set up some very local analysis near the event horizon.
Yes.
There's a very local criterion near the Cauchy horizon.
Yes.
And you're going to connect the two by solving the wave equation.
Yes.
From one to the other.
Yes.
Okay.
So yes.
In this equation you have written the chi will be 0.
Yes, that chi will turn out to be 0. In fact, C1 is also 0 because we know that alpha dagger alpha tilde is 0. So in fact, what we can show is that alpha tilde psi is just e to the power minus pi omega naught alpha dagger acting on psi.
It's basically like Hawking's calculation, but instead of going from the event horizon to infinity, you're going from event horizon to Cauchy horizon.
Some sort of a ray tracing which is solving the differential equation.
Yeah, but I was wondering whether he's going to do ray tracing a little.
No,
WKB?
so for example, if you're looking at just Schwarzschild black hole, then we don't even have a Cauchy horizon. Then we can do this.
Yeah, you can do it, but I suppose your interest is in the Cauchy horizon.
Yeah, our interest is in the Cauchy
And
horizon.
when you solve this wave equation, presumably, can you solve the wave equation?
We can solve the for BTZ we can solve it exactly,
Okay,
but
you said you can solve it exactly.
yes.
But in general, you cannot. presume.
So we can do numerics.
So that's what these guys did. I mean, Harvey and collaborated. Right?
Yes, they solve the wave equation.
So taking their result, you want to put this in
Yes,
and see what.
Yes.
Oh yeah, good. But why can't you solve the wave equation even just for Reissner Nordstrom in
we can
minimally coupled scalar field in Eddington-Finkelstein coordinates, for instance, you can, right?
we can write down the equation. We can't. We don't have some
But
solution.
it's solved in terms of an integral.
Yeah, in some sense, yeah. So,
Okay.
yeah, that we can evaluate numerically.
Looking at essentially the temperature of the Cauchy horizon,
Yes. So this is the temperature of the Cauchy 2 pi by kappa minus.
and if you do, what do you get?
So for the BTZ case, we can just compute this k1 and k2, and then it turns out that this is exactly correct.
I have a question. So the mode B is like a very nice ingoing mode near the future event horizon, and you have computed k1 and k2 near future event horizon. But as you go from future event horizon to
The
Cauchy,
mode B is at the Cauchy horizon.
But what Indranil is saying is that it's going into the event horizon, and it's a mode that's potentially funny near the Cauchy horizon.
yes, this is what I was expecting. So where did you fix this k1? B is nice and regular somewhere. Right?
B is at the Cauchy horizon, the mode expansion would be B into, let's say, u to power plus minus, something like this.
This CH plus is the right.
This.
Right.
This CH plus. So, and because this is the mode which will which we will get when we do the integral as we defined for alpha. So once we are doing that integral at the outer horizon, and to extract A's, to extract B's, we are doing that the integral at inner horizon.
Now, in the case of BTZ,
Yes.
this is some orbifold of ADS.
Hmm.
So you could just compute the 2.5 function directly without all of this?
Yes.
So isn't that easier than all of this? Why do you need all these modes? And
For BTZ, it is easier. But let's say we want to do it for arbitrary black hole,
okay, you want
high dimensional black hole. Then that calculation is much more difficult than this. This is just solving a wave equation and we get this.
Still didn't understand the question. What is the analog of solving the differential equation in 2?
Here, so I haven't shown it, but we can. So if we want to relate B and A,
This is the first thing that I want to do. That I relate B with A, and then with this relation I want to compute this relation.
yeah,
And
and check
if
this.
it is
whether-
right or not.
Yes.
This is what I want to do.
Yes.
So you want to first relate B with A.
Yes. So to do that, you need to solve the differential equation in region 2.
To do with that, I just need the definition of the B modes. Then I can compute that, and then the modes I need to follow those modes as I.
Yeah,
go
that
from-
is solving the differential equation, right?
That is the part which is solving the differential equation to see what those modes become on the
Exactly.
Cauchy horizon.
Yeah. So rather you start with, let's say, Cauchy horizon, and then see what it happens. Yeah. So that will fix these K1 and K2. Right?
So you haven't solved the differential equation yet. You will say something. Right?
No, I'm just telling you. I won't solve it here, but I'm just telling you for BTZ, we can do this, and we can check that this is indeed true.
right.
But for others, it will not.
Which is that you can do it analytically, right?
For analytically. For RN ADS, we have checked numerically that this is not true.
This is what you expect from the conjecture also.
Yes.
So what was the Rial's conclusion for
Rial's conclusion for BTZ was that it's smooth if it's close to extremality.
And smooth means violent.
Smooth means violation of cosmic
here,
symmetry. So
Consistent.
it's consistent, but it's just that we don't have any extremality condition. And in fact, it looks like this is kind of the smoothest possible state at the inner horizon, so we don't really understand why that condition is important.
So again, what was the last?
If B dagger is exactly this, then I would have thought that that is the smoothest possible state we can define on the inner horizon, defined with respect to these expectation values. So the fact that stress tensor diverges is something which I don't understand.
Is it like
Sorry, their case diverges. It doesn't
Diverges for non-extremal black holes.
Yeah, so in your case, it doesn't happen even for non-extremal.
So we haven't computed the stress tensor, but this
So
thing,
This kind of thing doesn't.
yeah,
happen in
this
non-extremal cases.
this is always true, irrespective
but
of.
so far, in a way, you're working with just the vacuum, right? This calculation would be
Yes.
the same for the vacuum and for perturbation. They presumably found some funny stuff when you added some perturbations, right?
So the funny stuff was for the perturbation.
Was the perturbation.
Was
But
the perturbation.
now what they're doing is they're looking at the quantum expectation value
Yes.
of the stress tensor. So far, the calculation doesn't care about perturbations.
Mhm.
Basically in the vacuum, right?
Hmm.
Now, Rial, I can't remember the quantum part what they did, but they were looking at perturbations. So you should
At
expect
quantum part, they just computed the stress tensor.
in what state?
In I think in similar kind of state, just this kind of state.
This quantum stuff.
Yeah,
Yeah.
I was away.
Yeah, he said it a bit fast. I can't remember.
So
But he'll remember. Yeah.
yeah, so that is I think in this
This
this calculation.
But with perturbation or not?
No, I don't think
Without.
it's with. Yeah,
Just in the vacuum.
yeah, I
Okay.
think so.
So good. So stress tensor does not. It's totally smooth. What you're saying is the state that is basically the thermophile double state is as smooth near the event horizon as near the Cauchy horizon.
Yes.
It's a fantastic statement. Okay. Now, though a small perturbation
Yeah.
could change that.
Definitely.
the first
No,
statement
but I
I'm not
thought Rial
totally sure.
said that even without perturbation, the quantum expectation value of the stress tensor goes up. That's what he's saying.
Blows up. Did he say that?
No. Stress tensor was finite for BTZ.
Finite.
Yeah.
But
but
non-extremal case.
for non-extremal, it was infinite. So he had this.
You're doing non-extremal, right?
No, I'm doing anything.
Fine. In particular
In
non-extremal.
particular,
Yeah.
non-extremal.
Yeah.
Right? Yeah,
So,
there is a
There's a tension.
Yeah, there's a tension. And so
what's the other?
yeah, I don't know.
But your
I mean,
statement
their thing is coming from the fact that the bees get extremely energetic, right?
yes.
Because of the late time,
Hmm.
slow late time decay,
Yeah.
and that is not seen.
Yeah.
So the infinite stresses would have meant some infinite temperature or something like that, right?
He is not taking back.
But
That was the classical analysis.
I don't see any sign of that.
Okay.
So that was the classical analysis. But
So what was the rationale for the blowing of the stress tensor?
So,
common case? In the vacuum?
they just computed the stress tensors. So they also computed 5.
Same as your calculation, right?
Yeah, it should have been same. I mean, yeah, but they had some mode sum, and they showed that for that particular constraint beta less than 1 or something, this would diverge. This sum would diverge. Otherwise, it won't.
So you're saying it's not a contradiction because you haven't yet computed the stress tensor.
Yes, but we don't.
But since you've got the perfectly smooth state.
Yes, that is why. So that is why.
Hard to believe you'll
Yes.
get a divergent
So,
stress.
Why do you
yes.
say perfectly smooth state? This is the first way I'm trying to understand.
Because of this.
Computation, how much does it prove? Does it prove the whole smoothness or does it just prove the complexity? This is the first question.
Well, let's try to make let's try to go to that Cauchy horizon and make the smooth state. By which I mean the smooth state where if you took slice like this and put it in the usual vacuum. Okay.
He is doing all the calculation in Hartle-Hawking double so far.
Yeah. But suppose for a moment we were to define the perfectly smooth state. I want to define perfectly smooth state.
Okay.
Perfectly smooth state for me, if you don't mind, I'll just
Yeah.
Different
is a state where you slice like this and you quantize in the normal way. Okay, this is time, this is space.
Yes.
You ask for the usual vacuum. That is my definition of perfectly smooth.
Yes.
Which is Hartle-Hawking double in this?
Which is if the thermophile double here is the thermophile double here, is the perfectly smooth state here.
Yeah.
Oh, it's above. Okay.
Yeah.
Yes.
I'm sorry.
So this is my criterion for perfectly smooth. Now, perfectly smooth completely determines what is happening here, what the correlation functions
Yes.
are here. So if you presumably if you find the same correlation functions here, you are in the perfectly smooth state. Now you're questioning that. One could try to be more careful.
And there are the second question is about two sectors. One is the gravity sector, and other is the matter sector. So first, if your matter stress tensor is too high, let's say, then you need to take into back reaction into account, and then that might do something funny to your metric.
But let's say just in the comparison with what Riya did.
Yes.
Presumably what he did is do a scalar calculation
Yes.
and computed the stress tensor
Yes.
of the scalar field.
Yes. Exactly.
Neither side has taken back reaction into account.
Yes.
Right. So this will be just exactly this kind of.
This calculation.
Yeah, but there's a difference.
So somehow it would be the statement that you're not in the perfectly smooth state, right?
Yeah, it could be, or yeah, or there's some issue with regularization.
Do this kind of thing, right? So what is their conclusion that if the stress tensor diverges, the metric is still continuous or not? Maybe it's not second order. Maybe you cannot differentiate.
So Harvey-Rial's conclusion was.
It will be smooth, and then your thing will be consistent with that.
But I can't understand how the stress tensor could diverge at all.
Yeah, that
It's
is
just
a
a
good.
local quantum field theory statement. You're in the perfectly smooth vacuum, stress tensor should not diverge. But it sounds a little bit like these guys are concluding that they're in the smoothest vacuum you could possibly make
Yes.
there. Or at least that you could fix modes here so that would be true. Because really in some way you have access only to here.
Yeah.
But you don't know what's happening here, but since you're totally ignorant here, you could fix it up here so that you're in the perfectly smooth state. This sounds like what?
Yes.
Sorry.
Here, if he computes the stress tensor, if he computes the matter stress tensor, in this computation, everything is in proof approximation.
Yes.
Then, if he is doing for BTG to begin with,
Yes.
then the claim would be that this is totally smooth. There is no problem.
I would imagine. It looks like
This is
Yeah.
also your claim, right?
Yeah, it looks like it should be.
And then what is the contradiction?
the problem is that people are saying, I don't remember this, but that Harvey concluded that
Yes.
away from extremality, they've done the calculation,
Yes.
and in some cases they find not a blowing up stress tensor.
Yeah.
Their claim is in BTG, away from extremality, it does not blow up.
Whereas
But then-
Harvey claims that in BTZ, away from extremality,
It blows up.
it blows up.
It's opposite.
I can't believe this is. Have we said this?
Even I can't remember. But
Because
Yeah,
I was not there, but that
Yeah,
before
so-
he said that in BTG it is not satisfied. That means that presumably it is smooth.
yeah.
Yeah, but there was a constraint which was something like
Later he talked about
this. No. Even in classical thing, there was a constraint which was this beta, and beta
Classical analysis rested on, of course, this perturbation.
perturbation. But
It
yes,
is basically-
but in both the cases, he got this condition that if this beta was delta over r plus over r minus 1. So only under this condition was a strong cosmic censorship violated, otherwise not. So
This condition is satisfied.
satisfied.
Other
Yeah.
one-
Other would violate, yeah, exactly. So this condition we can't see here.
What
That's all
your
I'm
claim
saying.
is that I can do a purely classical calculation and see that in BTG this is smooth and other cases it is not. I don't even have to do any quantum calculation. This is what your claim is, quantum.
It's a quantum calculation.
When I say classical, I mean just a proof approximation to see the stress tensor. This is you are making this claim and which is slightly different from the other.
It sounds like it's a direct contradiction, right? It sounds like both groups are doing the same calculation and getting a different answer.
How strongly can we say that if this is true, then the state is...
That's
Yeah, that is the question.
Because this derivation was in the other direction.
Yeah.
You assume
Yes.
a perfectly smooth state and then you...
Yeah, but now let's suppose we want to compute something about the stress tensor. If you know everything about the 2-point function of phi, we know everything about the stress tensor.
Yeah,
The stress tensor is defined by taking two phis, putting some derivatives and taking them together. So you would have to see some deviation of this 2-point function from perfectly smooth.
So is this related to the kind of question that Surat was asking?
Yes, exactly. That is why he was asking about this subtraction of counter terms.
Subtraction. Because you see, when you say Shiva, that you regulate, right? What are you subtracting? Are you subtracting
Yes.
the full divergence or the little bit of divergence?
Yes.
The little bit
Yes, that is why.
So you have to, what is the reference subtraction scheme?
Yeah, so you need to define your operator.
The composite operator.
No, natural.
So that's where I.
So that is why probably he was saying that we probably need some subtraction which which depends on this.
So I think the way Harvey was doing it, some divergence was left still.
Yes. Yes, that is the claim. Yeah.
Yeah.
So that would imply something about the irregularization of stress
Draw a
tensor.
critical conclusion by some choice of regularization. Is this natural or something?
So that's one. He was arguing for a particular natural scheme, while Surat differed on that. I thought
Yes.
that yeah.
And it sounded like what Harvey said was reasonable.
That's yeah. You said something before. I forget that.
But all this abstraction is for quantum calculation.
So
At
the way
classical level, do they agree or not? At the classical level first.
What do you mean the classical? This guy's only doing one.
Classical,
Yeah.
there is no issue in this in vacuum state.
actually the way they computed the stress tensor was they computed the 2-point function, subtracted of the divergent part, and so they had this z0 coordinate which was and so they had something like this.
Subtract. The subtraction should not depend on where you are.
On the state. You want to do a local subtraction that is generally coordinate invariant.
Yes.
That is somehow universal. Subrat was saying, suppose you just subtract away the expectation value in the thermofield,
Yes.
which of course doesn't sound reasonable, right?
Definitely. Because that typically cares about the state.
Yeah,
You're losing all the information.
I mean that sounds like a very particular thing to do. But if you just subtract away what we try to do normally is subtract some sort of covariant local counter term.
Yes.
Okay.
Right.
And it sounded roughly like what Harvey was doing.
Yeah.
But then what you're somehow saying is that, okay, so that this 2-point function,
And none of this calculation cares about back reaction. Right? This is what I
Yeah.
was quantum. You don't even care about back reaction.
Yeah.
no, nobody's taking that.
Okay. I didn't
Yeah.
know the last I missed.
Yeah. It's interesting. Then it's just about a subtlety of defining the stress tensor,
Exactly.
rather than about any dynamics.
Yeah.
But that is, I think, the crucial also, right?
Yes.
Typically, that's crucial because how are you going to distinguish Cauchy horizon if you just go there and do this calculation corresponding? It's about how you follow, how you get there.
But
with
what
your-
is the
with
difference
your
between the
energy
Cauchy?
operator?
What is the difference between the Cauchy horizon and the event horizon locally?
Just the temperature. That's
No,
all.
but not locally. That's as you go there, you have some energy. As you go there, what happens to that? Right. So So that's your definition of energy. If you're an observable there itself, then you could.
No, but let's suppose I'm trying to define the local value of the stress tensor.
Yeah.
That is a local question.
Yeah, but it should be independent of the state.
Should be independent of the state. So I've got my subtraction. I've got my counter term or whatever it is. That will be as well defined. I mean, if you cannot subtract away the infinity here,
Yeah, then
why could you do it here?
Exactly, that's the question.
They sort of seem identical. And logically.
Yeah,
You can
Exactly.
come
That
up
is the-
with a
that is the question.
possible counter term, like one has counter term and try to repeat the calculation to see.
Yeah, and that is what Harvey claims, not by himself, but using earlier work
Yes.
to be doing.
Yes.
Of course, this is all work by these GR people who may or may not be.
But in fact, Surat also agreed. I think that it's a state-dependent subtraction that you're doing the state.
We are not computing the
We've not
stress
done it.
tensor, so it's just speculative.
But the question is whether what Harvey is right. Maybe it's not. Maybe you know, these are very subtle. These are very easy to get.
But do we know that the two-point function in the BTC diagram has this universal form?
Yeah, I mean that is what we. Sorry.
Compute it using this or before techniques.
Yeah, I think it should match, yeah. Because
Maybe it's a different. It could be a different form that still gives that answer.
Okay, but it would be very easy to check.
Right.
Because I think this is what I also feel. For the particular case of BTZ, the simplest thing to do is take the Euclidean two-point function
Yes.
and analytically
continue. Yeah.
There's no issue there. It's a very easy thing to do.
Yeah.
And that, if it's perfectly smooth, it's perfectly smooth, right?
Yeah.
And that's what you're saying. Can you check it that way as well?
No.
I think it's working. I mean, it will be easier than all of this in this particular case.
So, but that still will be the two-point function, right? This
Still will be two-point function.
Yeah, I think Harvey's claim was that two-point function is fine. Is always fine. It
It's
doesn't.
fine.
Yeah.
It's not a question of finiteness. I think Naveen's wondering whether it could be that there is a subtle chain difference between the two-point function here and the perfectly smooth, right? And that subtle difference is that you don't somehow see it leading order,
Maybe.
and is the reason for the divergence. Is that accurate?
Yeah.
Okay. But that would be very easy to check. Okay, very interesting.
Just one last thing. I was talking about this operators behind the horizon. So the claim is that if we want to find this operator, which is correctly entangled with the operators B, then we cannot use. We will have to reuse these old modes. We can't define the new modes. These new modes won't have correct entanglement with B.
How do you fix K3 and K4?
K3 and K4 we can just fix by
Demanding this condition?
yeah. So demanding something similar to this.
Demanding this B times BC commutator is this. How are you fixing K3?
Yeah, by demanding BC expectation value.
E must vanish. That's what you're saying.
Yes. So essentially, what will happen that we can set K5 and K6 to 0. So this won't really play a role in entanglement. So this is important.
And then you will argue this is clearly unphysical, therefore this cannot be satisfied.
No. We are saying that we can satisfy this. We can satisfy this with a particular choice of K3 and K4 in the case of BTC.
In some sense expected, right? Because then you're saying that if there are no modes, no additional modes there,
Yes.
then you can make everything smooth. Which would be
Yes.
you should expect, because the issue was that the issue determinism comes from the stuff.
So as long as
E and D modes,
yes.
which are not causally connected.
And what is the statement in higher dimension?
This statement is for any dimension. So if
No, you are saying for BTC.
yeah, so for higher dimension asymptotically ADS Rn black holes, this statement was not true. But suppose this statement is true for some other black hole in any dimension. Suppose this statement is true, then what we are saying is that there is possible to construct some K3 and K4 such that B and C are correctly entangled.
So it's not possible, you're saying.
It is possible if this is true.
But the first statement itself is not true.
In asymptotically ADS Rn, but we can do this computation for de Sitter Rn where probably it's more interesting.
Apart from BT, higher dimensions, why should I expect this BC computer to be this nice thing?
Because of, I mean, so the question is whether we should expect or not. So if strong cosmic censorship is violated, then we should expect this.
Yeah, if it's smooth.
If it's smooth,
Definitely.
yes. So the question is, how do we test?
Okay.
So the
Strong one violated, okay. Yes, then you expect.
so
But
the
if the weak one is violated, but still not, let's say, in a weak manner.
no. So for this, we only assumed C's continuity of the metric, not differentiability. So any violation would come in here.
But you are saying generically it holds, because generically you would have.
No, we are only saying that for ADS Rn black holes. We haven't done the we haven't checked this for de Sitter Rn black holes.
Generically meaning, you have to tune this, right? You have to tune this.
Yeah, we have to tune this K3 and K4.
Not K3, even K5, K6.
K5, K6 won't contribute. So the point is that we can check that norm of K5 and K6 would be just 0.
But that is why you are getting this correctly, right?
Yes, in some sense, you can say that. So if we, yeah. So basically, what we are saying that if we want to extend beyond the inner horizon, then we need to reuse these modes. We cannot define new modes.
Yeah.
So this is kind of a prescription.
Can you prove that by keeping K5 and K6 non-zero, also there is no, if I keep them non-zero.
So what will happen is that these K5, these D and E dagger operators are not correctly entangled with A and A tilde and A dagger. They actually are not at all entangled. So expectation value of D, A tilde, or all such expectation value would be just 0. So and moreover, so that is why we don't want these modes.
But then we could keep kappa 5 and kappa 6 arbitrary and still get C equal to this.
So what will happen is that we can check that kappa 5 squared minus kappa 6 squared would be just 0. So this won't really contribute to the norm of this rate. So so essentially we are, yeah. So with
You also want CC dagger to be of some universal form, is that right?
yes.
Okay, that's where that condition will enter. Because in CB you will never see kappa 5 kappa 6.
Yes.
If you do a classical calculation, forget this all quantum mechanics and A dagger. If I take Einstein's equation
Yes.
with right kind of boundary condition, if I try to solve it
Yes.
and try to see what happens to the classical stress tensor on
Yes.
this
Yes.
on Cauchy
Yes.
horizon, and not BTG but others,
Yes.
higher dimensional ones, what would be the claim? That matter stress tensor diverges? The
For
classical one.
for ADS Rn, I think that was
Yes,
Harvey's
ADS,
claim.
RN.
Yeah, that was Harvey's
Claim
claim.
is that for the large L modes of the stress tensor diverges because these
They
large
will
L
stay
modes.
for
Yes.
long time, they give the left-hand radius and the divergence. Okay.
Yes.
Now the same, so this was totally classical. Now you
Yes.
said that I want to do a quantum calculation, which is this one,
Yes.
but in probe approximation, and then there is some regularization scheme, and depending on that regularization scheme, either you,
There's no regularization scheme here. I'm not computing the stress tensor at all.
okay, so you are not computing stress tensor at all, but for this, where is the deterministic tensor? What would you say that I didn't understand your statement. For higher dimensional ADS Reissner Nordstrom,
Yes.
what is your claim? BC commutator can be made the right kind of form by choosing.
No.
Firstly, just from outside in high dimensional ADS, Reissner Nordstrom, you're seeing a divergence. You're seeing something funny.
Yes.
The 2-point function, forget about region 2 prime.
Yes.
Just in region 2, the 2-point functions are not right.
Yes.
So you're going to have lots of problems.
Yes. This is not right.
That's the zeroth order statement.
Yes.
For that also you are saying.
Yeah. We can check this. This is not right for Rn ADS in high dimensions. Yeah, in any dimensions.
So everything else is some
Yeah.
small subtle thing which
Yes.
we forget about, right?
Yes.
So the first, this BV dagger is always
Yes.
So even without a classical perturbation,
Yes.
quantum mechanics is making the Cauchy horizon singular in higher dimension.
Yes.
I think that is a very clear thing.
Yes. And this can be easily, this test can be easily implemented for even de Sitter black holes. And even actually, even for just Schwarzschild de Sitter black holes, we have 2 horizons, so maybe it will, even there we. How does this? Sorry, what looked at?
What replaces this form?
I don't know. We have some numerical resulted.
Oh, no.
Yeah.
But you know, there is an
You
added.
you have things going to infinity.
Things. So we computed this numerically, and numerically we can see that. So suppose we compute this. This is not equal to 0, and a question could be, how do we know that our numerics are reasonable or not? So we expect this to be 0 for large angular momentum modes. That we can check by using a WKV approximation and solving the wave equation in region 2. And we indeed find that our numerics give this to be 0 for large angular momentum modes.
Classically, you are finding first derivative is bad. Totally classical calculation, you are finding first derivative is bad from the left time radiation from region 1. Now here quantum mechanically B's are like, every B is like first derivative of the field. Roughly it's like the first derivative. So you are again finding the B dagger, that quantity is bad.
B, I'm not sure if I would think of B as the first derivative of the field. I mean, I use that to extract the mode, but these are just annihilation operators.
It sounds like the quantum answer is finding opposite behavior from the classical one, because he's saying that there's no trouble at large L.
Yeah. So, but large L.
Large L, why is L? This whole calculation forgot this gray body factor. Why is L in this?
No, there's L. There can be an L. There can be an L.
Yes, and then how does it change
This-
the right hand side?
So we can check that if we do this computation for large L, then in the limit L going to infinity, this is exactly this. You can do that. I'm not forgetting about it.
L goes to infinity, the quantum state reduces to the limit.
Yeah, but that is expected. So even actually there was a that is a statement that leading order divergence vanishes, but not. It is still consistent with. Could still be consistent with.
Why did it have to work just in WKB? You
Yeah.
use large L just to justify that WKB. Right?
Yes.
So you're saying in WKB, this criterion that you set up
Yes.
is satisfied miraculously.
But only for large omega, it won't happen.
Okay,
in
but
the
where it's satisfied, why is it satisfied? You have an intuitive explanation for that?
You said you expect.
We expect. I should have phrased that better. There have been previous studies which shows that stress tensor, leading order stress tensor, doesn't diverge at leading order. Leading order divergence is 0 rather. So they are subleading divergences. So yeah, I don't know. We didn't expect this initially, in fact, but yeah, this is what we did. This is something. So this is something which is true. For example, even independent of the form of the metric f of r. This is always true. So, yes, in large L limit.
Could it be that large L sets the potential very high and
Yes.
that gives you the red shift and that fights with the blue shift. Therefore, at very large L, in some limit, probably you will see that this is still nice.
You're saying that f of r becomes irrelevant at large.
Yes.
That all
Only-
the
only-
potential
yes.
is coming from the centrifugal force.
Right,
Yes.
right. And then therefore, and how much that is justified, I don't know. I mean, taking naive large L probably show this, but I am not totally sure that all this order and it will work.
Okay, if we want to get lunch, we better.
Let us clap for the
Thanks.